So today, I'm going to be finishing up section 2.3 and moving on to 2.4 and 2.5. Speaking of that, I'll let you know, if you come over here to your assignments or your modules, that's probably a better place for me to look at for stuff like that. All right, so you got homework number 3 right here. You also have your traditional homework number 3 and your homework number 3. I wasn't paying attention to this, and if you actually noticed, I put the due date as October the 11th. Sorry, that's fall break. 10th and 11th is fall break. I didn't mean to do that. I was just looking at a calendar going, that's a good spot for it. Okay, so I pushed it back to the 13th because Jacob's request. So instead of pushing it forward, I pushed it back to the 13th. That's the Thursday when we get back from fall break. So let you guys know. Said that has been noted in the due dates and stuff like that. So it's actually due on the 13th. The traditional homework is due at the beginning of class on the 13th, and the online homework is due at 11:59 on the 13th and stuff like that. I always said 11:59 because you can't do midnight. So there you go on the computer system. Does that make sense? Questions? All right. So I did have pay attention to that. So. All right, so let's come over here and let's talk about this. Now, by the way, that traditional homework and online homework is material from section 2.1 through section 2.5. So I hope to be finished with that today, but what I don't get to today, I will get to on Monday, on Tuesday, so you should be able to pretty much do most of your homework. I know right now you can do about 50% of your homework, if not a little bit more than that, maybe 60%. Homework based upon what we've covered so far. But there's this last little bit from section 2.5 on LU decomposition, LU factorization, and some of the other things that we're doing. So I did put some questions on that, and we'll be hopefully going at least starting that stuff today. So let's come over here and pick up where we left off, and that is we were talking about how to calculate an invertible matrix. Now remember, not all matrices are invertible. First things first, when we're looking at invertible matrices, they got to be square. You're dealing with square matrices, okay? Second thing, if it is going to be an invertible matrix, then we call that non-singular. Invertible matrices, if A has an inverse, A is called non-singular. If A is not invertible or does not have an inverse matrix, we call that a singular matrix. Again, terminology. All right, so here are some of the properties. This is theorem 8, properties of actually being a matrix being invertible. So it says this, theorem 8, let A be a square n by n matrix. TFAE. TFAE means the following are equivalent. So if you got one of these things, you got all of these things. Is an invertible matrix, aka matrix A is non-singular. Then the rest of these things are going to be, or what's going to happen? A is going to be row equivalent to an n by n identity matrix. Because how do you actually create the inverse? You take A and you augment, which is n by n, you augment it with the identity, n by n identity, and then you row reduce A to the identity, and I will keep up with that and actually turn into the inverse. That was our pattern that we did last time. So A is going to always be row equivalent to the n by n identity matrix. And if it's row equivalent to that, that means A has n pivot positions. Okay? And there'll be 1, 0, 1's on the diagonal, 0's off the diagonal. There's your n pivot position. The equation AX equals 0 has only the trivial solution. So if you ever set AX equals 0 and it has the trivial solution, then you automatically know that A is going to be invertible. If you have more than just a trivial solution, if you got the trivial solution for maybe an infinite number of other solutions, then A is not going to be invertible. Does that make sense? That will be a singular matrix. But if AX equals 0 has only the trivial solution, then A is invertible, and there's row equivalent to all the following are equivalent. The columns of A form a linearly independent set. we look at the columns of A's as vectors, these columns of A's will be linearly independent. So if I got a matrix, n by n matrix, where all the columns are linearly independent, I know that that matrix that's representing these vectors is going to be an invertible non-singular matrix. Linear transformation, x going to a times x is going to be 1 to 1. Okay, so if you look at, you remember, any linear transformation can be written or be represented by a matrix. If a linear transformation is represented by a matrix, A, and then if A is invertible, then the linear transformation is going to be 1 to 1. And it goes the other way. If you've got a 1 to 1 transformation, then the matrix it represents is going to be 1 to 1. Okay? Again, you have, remember, A's got to be an n by n matrix here. The equation AX equals B has at least one solution, okay, for each B element of Rn. You'll be able to solve AX equals B. Okay? Now, the columns of A will actually span, remember our definition of span, all of Rn. Okay? So remember, A represents n by n's. The columns of A are linearly independent, and the columns of A are actually going to span all of Rn. Okay? Again, tying all these things that we've discussed before. The linear transformation going from x to a times x maps Rn onto Rn. Okay, so let me put this in English. If A is an invertible matrix, remember it's n by n, and A represents a linear transformation, that linear transformation is going to be 1 to 1 and onto. It's 1 to 1 up here, and it's onto here. You get both of them. It's going to be 1 to 1 and onto. Okay? Again, this is a little bit of overkill, but here it is. There is an n by n matrix C such that C times A is equal to the identity. There is an n by n matrix D such that A times D is equal to identity. And by the way, C is going to actually be equal to D. It's called the inverse. That's what the inverse really does. And number 12 here is this. If A is an invertible matrix, A transpose, change the rows to columns and the columns to rows, is also going to be an invertible matrix. Is also going to be non-singular, to use our terminology here. Again, just want to remind you of this. How do we actually find the inverse of an n by n matrix? Okay? You find the inverse of an n by n matrix by taking A, which is square, remember, augment it with the identity, and that's going to be squared. It'll be, this is n by n, the identity is going to be in, or n by n identity. And when you do reduced row echelon form, you take A and start row reducing and sweeping down and making pivots and making zeros, that the A will turn into the identity because it's row equivalent to the identity. It'll have the n pivot points there. And the interesting thing, this is that classic computer science. The moves that you make will be stored with the identity and show up over here as A inverse. So this is actually how you end up figuring out what A inverse is. This, the identity will show up here, and what it's augmented to will actually end up being the A inverse, the inverse of matrix A. Okay? So, again, I know I'm fast on because I wrote it down before, so I'll put it up here just one more time to make sure you guys actually get a copy of it down. But the next thing I'm going to do here is practice. So let me give you guys a matrix, and let's go figure out what the identity is. Okay? That's good? Okay. Here it is. Find A inverse if A is equal to the matrix 0, 3, 6, 1, negative 2, 2, negative 4, 6, negative 2. All right. To find this inverse, what do? I need to do this. I need to do A augment with I. First off, what size matrix is this? 3 by 3. Okay. So first thing you got to know, it's got to be square. It's a square matrix. So A is 0, 3, 6, 1, negative 2, 2, negative 4, 6, negative 2. I'm going to augment that with the identity. Well, it's got to be an equivalent identity, so 3 by 3. That is the 1, 0, 0, 0, 1, 0, 0, 0, 1 identity. Does that make sense? Now, what's my first move? Row swap. Which rows you want to swap? 1 and 2. R1, R2, row swap. Okay? So that would give me this, because you want to make sure you have a pivot up here. That's a 0. Zeros are never pivots, so you got to row swap with somebody. My choice is going to be row 2 because it's already got the 1 there. So that's going to give me 1, negative 2, 2. You do the entire row here. 0, 1, 0. And then 0, 3, 6, 1, 0, 0. And the third row stays the same. Negative 4, 6, negative 2, 0, 0, 1. That makes sense. Have I lost you anywhere? All right. What's your next one? Sweep down. Take 1 and go after that negative 4. You already got a 0 there. So, again, I'm just going to put a little line right here because I got some room. I'm going to multiply 4 times row 1. I'm going to add it to row 3, and I'm going to replace row 3 with that. Okay? So, that is going to give me this. Row 1 would stay the same. 1, negative 2, 2, augmented with 0, 1, 0. 0, 3, 6 would stay the same. 1, 0, 0. But here we go. Net 4 times 1 is 4 plus negative 4 is 0. That was the point. 4 times negative 2 is negative 8 plus 6 is a negative 2. 4 times 2 is 8 plus negative 2, or 8 minus 2 is positive 6. 0 times 4 is 0 plus 0 is 0. 4 times 1 is 4 plus 0 is 4. Okay? And 0 times 4 is 0 plus 1 is 1. And notice how that 4 is being stored in terms of row reduction type thing here. So far, so good. Okay? What would your next move be? Make that 3 a pivot. Because I want to be able to kill off that negative 2, so you want to pivot first. So I would multiply by 1/3 times row 2. Replace row 2 with that. So this gives me 1, negative 2, 2, augment with 0, 1, 0. 0, a third of 0 is 0, a third of 1 is, a third of 3 is 1, a third of 6 is 2, a third of 1 is 1/3, a third of 0 is 0, a third of 0 is 0. Yes, it doesn't take long for fractions to show up in this mess. Okay, let's keep going. And then just recopy, third row. 0, negative 2, 6, 0, 4, 1. Okay? What's my next move? Sweep down. 2 times row 2, add it to row 3, replace row 3. This would give me 1, negative 2, 2, augment with 0, 1, 0. 0, 1, 2, 1/3, 0, 0. 0 times 2 is 0 plus 0 is 0. 0 times 1 is, 2 times 1 is 2 times 0 is 0 plus 0 is 0. 2 times 1 is 2 plus negative 2 is 0. That was the point. 2 times 2 is 4, and 4 plus 6 is how much? 10. All right. No fractions. 2 times 1/3 is 2/3, plus 0 is 2/3. 2 times 0 is 0 plus 4 is 4. 2 times 0 is 0 plus 1 is 1. And there, I've got that. What's my next move? Make the 10 into a pivot by multiplying it by 1/10. 1/10 times row 3, replacing old row 3 with that. That is going to give me this. 1, negative 2, 2, augment 0, 1, 0. 2, 1/3, 0, 0. Here we go. A tenth of 0 is 0, a tenth of 0 is 0, a tenth of 10 is 1, that was the point. 1/10 times 2/3 is what? 2 goes into 10, 5 times, that'll be 1/15, good. 1/10 times 4 is what? 2/5. Reduce your fractions. And 1/10 times 1 is 1/10. So far, so good. All right. Now, what do I got to do? Sweep up. I'm going to do 2 moves at once here, so I'm going to multiply -2 times row 3, add it to row 2, replace row 2 with that, and -2 times row 3, add it to row 1, replace row 1 with that. So out of all that, the third row, that's 0, 0, 1, augment with 1/15, 2/5, 1/10. Okay? So when I sweep up, let's see what we get here. I got 0, 1, -2 times 1 is -2 plus 2 is 0. -2, okay. -2 times 2/15 is -2, -2 times 1/15 is -2/15 plus 1/3 is equal to a 1/5. Okay. -2 times 2/5 is -4/5 plus 0 is -4/5. And -2 times 1/10 is -1/5 plus 0 is -1/5. Does that make sense? I'm afraid, be careful, use your calculator to double check me on this, but I'm now using the fractions, so I go a little slower. And then I'm going to sweep up and kill this guy off, so this would be 1, -2, because these are both zeros. -2 times 1 is -2 plus 2 is 0. -2 times 1/15 is -2/15 plus 0 is -2/15. Okay? -2 times 2/5 is -4/5 plus 1. 1 minus 4/5 is 5th. And then the last one here is, what is 1/10 times -2 is a -2/10, which is -1/5 plus 0 is a -1/5. Does that make sense? I've got one more move to make. What's my next move? Okay, take here and sweep up. So that would be +2 times row 2, add it to row 1, replace row 1. So this is going to give me, and I'm just going to move them down here. So this would be 0, 0, 1, augment with 1/15, 2/5, 1/10. Right? 0, 1, 0 with 1/5, -4/5, -1/5. And here we go. -2 times, positive 2. Positive 2 times 0 plus 1 is 1. 2 times 0 is 0 plus 1 is 1. 2 times 1 is 2 plus -2 is 0. 2 times 0 plus 0 is still 0. And here we go. Okay? 2 times 1/5 is 2/5 plus a -2/15 makes it a positive 4/15. 2 times a -4/5 is a -8/5, and a -8/5 plus 1/5 is a -7/5. And then the last one here is 2 times a -1/5 is a -2/5, plus a -1/5 makes it a -3/5. All right, so there it is, which means, therefore, 3 dots in a triangular fashion means, therefore, to what's actually my matrix. We started with A, augmented with I, and then we row reduce, and we got I, so this becomes A inverse. It is 4 negative 7/5, negative 3/5, 1/5, negative 4/5, negative 1/5, 1/15, 2/5. Does that make sense? Now, I got a question for you. So now we're going to solve this equation because I want you to actually see what I'm going to do with this stuff. But you see this stuff here? Could you make a careless error on this stuff? Oh yes. We all could have. You know, be honest with you, I pre-worked this problem with you guys to make sure I didn't screw up my fractions. But, you know, I'm on the test or whatever. I want to make sure I get it right. Now, I got to show my work. And here's my work. There's my answer right there. And I feel good about my moves and stuff like that, but I could have easily screwed up adding a fraction. How do you do it on a calculator? I want to show you guys this so you can actually double check yourself on the calculator stuff. All right. So the first thing you got to do is you got to enter in matrix A. So second matrix over there, I'm going to edit. I'm going to call him A right there. But what size was this guy? 3, enter 3. 3 by 3. My numbers are 0, 3, 6. You type it in row-wise. 1, negative 2, 2, negative 4, 6, negative 2. And hit enter. Don't hit enter after each one you put in. And now, I'm going to take this thing. This is very important. I'm quick on this calculator. I'm so quick, I will type in a wrong number on a calculator. I do this all the time. So the next thing I got to do is I got to train myself to check my answer. So before I find the inverse, I'm going to go back to matrix A, just under names, and call up A. It takes you to the home screen, and I hit enter. Now, I type this thing in row-wise. Now, this thing's only 3 by 3, but once I get to those 8 by 8s and 10 by 10s, you know, I have to kind of really double-check myself on this stuff. So, I'm typing in row-wise, so always check it column-wise. 0, 1, negative 4, 3, negative 2, 6, 6, 2, negative 2. Yeah, I'm feeling good about my typing abilities. Now, here's the beauty of it. You want to find A inverse, we'll go back and type in A, and I can just do basically just recall back down here. There's A right there. It's correct. And the inverse button is right there. You see that little -1 right there? You just hit that guy. That's A, and now it's in matrix mode because you're dealing with a matrix, even though that's supposed to be the reciprocal button there. But on a matrix, that's the inverse button. And the calculator knows that's a matrix A inverse, so I just hit enter, and there it is. Oh, it's all in decimals. Well, that sucks. So I can hit math, number 1, convert it to a fraction, and then I can really double check my answer to make sure I did not make a bonehead careless error. Okay? Double checking yourself. We all make careless errors. Again, what's the difference between me doing this stuff and you guys doing this stuff? They're not going to take away my doctorate degree because I made a bonehead careless error. You make a bonehead careless error, you don't graduate. But once you graduate, you kind of make that hurdle. They don't take away your degrees after that. So, watch the careless errors. When I was sitting right where you're sitting at, I had to do the same thing. I had to figure out ways that I would check myself because I was always making careless errors. Okay? All good math people do in my world. All right, so you just have the ability to stop and double check yourself. So I feel real good about my answer. Does that make sense? So once we did that, I want you to see application. So part B to this problem is I want you to solve, so I'm going to do this just to make it a little more clear for everybody. I want you to solve this system of equations. Here's an application of this inverse. So the first thing I'm going to do is I've got a system of equations, 3x squared, 3x2, I don't know if 2 came in there. 3x2 plus 6x3 equals 60. x1 minus 2x2 plus 2x3 equals negative 15. And negative 4x1 plus 6x2 minus 2x3 equals 10. First thing I'm going to do on a system of equations is write it as a matrix equation. The coefficient matrix is 0, because there is no x1, 3, 6, 1, negative 2, 2, negative 4, 6, negative 2. You're going to multiply it times the variables x1, x2, x3, and this will be equal to your solution to the equation that we're equal to 60, negative 15, 10. That makes sense. And again, I want you to notice that it's in the form of a times x is equal to, this is the b vector, this is the new vector. This is the same a as what we were playing with up here. Hint, hint, hint. All right, so all that work was not for naught. This is part B. So how would you end up solving for x? Well, we have the equation ax equals b. What gets rid of an a? The whole point of it, a inverse. The a is on the left of x, so you're going to multiply a inverse on the left of the ax. So the a inverse and the a can be right beside each other because they're going to cancel. A inverse times a is equal to the identity. And when you multiply something by the identity, you just get that something back again. So, but what you do to one side, you do to the other. A times vector b. A inverse times a is equal to the identity times x is equal to a inverse times b. But the identity times x. When you multiply anything by the identity, you get the anything back again. So that's just x is equal to a inverse times b. So, to solve for x, all I've got to do is take a inverse and multiply it times b. Well, luckily, we've already calculated what a inverse is. That was that 4/15, negative 7/5, negative 3/5, 1/5, negative 4/5, negative 1/5, 1/15, 2/5, and 1/10. Multiply it times b. Who's b? This is the b guy. Multiply it times b, which is your 60, negative 15, 10. Now, I work real hard at these numbers. Why? Back to whole numbers again. Think about it. So this would be equal to what? Now, this is 3 by 3, right? And you're multiplying it by, even though it's a vector, you can look at them as a matrix, 3 by 1. So what would your solution be over here? 3 by 1, right? So, rows by columns. 4/15 times 60 is how much? 4/15 times 60. You guys don't trust me, I know it, but I got 16, so let's try it out. Okay? 4/15 times 60. 16. Times column. Negative 7/5, always put parentheses around the fractions there, times negative 15. Well, that should be like 21. Yeah, it is, still is. Plus 21. And then third position to third position. Negative 3/5 times at a 10. And I end up getting a minus 6. So 16 plus 21 minus 6 is 31. So that's 31. Second row, column, 1/5 of 60. 5 goes to 60 how many times? 12. Good, thank you. Plus negative 4/5 times a negative 15. Negative times a negative is a plus. 5 goes to 15 3 times, and 3 times 4 is 12. Negative 1/5 times 10. 5 goes to 10 2 times, it'll be minus 2. And I end up getting what? See, double check myself on that one. Okay. Row by column. So, oh, wait a minute, this is, hold on. 1/5 times 2. So, 1/5 times that's 12. 4/5 times 15. So, I'm getting 22. Did you guys get 22? All right. And then, the next one is 1/5 times 60. 15 goes into 60 what? 4 times? Plus 2/5 times a negative 15. 5 goes into 15 3 times. Minus 3 times 2 is a minus 6. And then 1/10 times 10 is 1. So that'll be plus 1. And I end up getting negative 1. This ends up becoming the x solution. So in other words, x1 would be 31, x2 would be 22, x3 would be negative 1. Does that make sense? Now, if I was trying to, well, the other way you could have done it is what we did in chapter 1. I could augment A with this guy here, do all that beautiful row reduction, 20 minutes later, check on it and see how you guys are doing, and watch this answer actually pop out as identity ends up being equal to 1, 0, 0, 31, 0, 1, 0, 22, 0, 0, 1, negative 1. There's your answer. But once you've got that inverse, you've got all that information stored, you just got to slap him times, multiply times the b, which is what it's equal to, and that'll get you that a vector. Only if only if a inverse exists. Not all matrices have inverses. Does that make sense? Questions? So, this thing out of the way. So, and just one more concept on this stuff is this. Now, just want to put it in context, because we're always in the back of our mind talking about linear transformations. Any linear transformation can be represented by a matrix. So if we got these matrices that are now representing linear transformations, and they're square and they're invertible, what does that actually mean? It means this. Definition. A linear transformation, T, going from Rn to Rn, right? Rn to Rn. So let me stop there. If you're going from Rn to Rn, it's a linear transformation, then if there's going to be a matrix that represents this linear transformation, what size matrix would it be? Well, it's this n by that n. Remember, you have to read it in reverse. We used to have m by n, but this will be n by n. It's going to be square. If you're going from Rn to Rn, it's going to be a square matrix, all right? And is said to be invertible if there exists a function s, linear transformation s, that is from s going from Rn to Rn, and here comes your property, composition of two. S of t of x will give you the x vector for all x in Rn, and if you go the other way, t of s of x will be equal to x for all n. Because if these guys are going to be literally inverse functions or inverse linear transformations, they're going to be represented by, if A represents linear transformation T, A inverse is going to be represented by a linear transformation S. So when you put those two guys together, whatever you plug in for X is what you're going to get out for X. Does that make sense? They literally cancel each other out. So linear transformations can be invertible just as well as matrices can, because, think about it, any linear transformation can be represented by a matrix. So if the matrix is invertible, the linear transformation will be invertible. That's what this definition is actually saying. All right, so the other big thing that we've been focusing on here is this matrix multiplication, and notice how I beat that mess to death too. All right, so with that, section 2.4 is called partitioned matrices. All right. Partition matrices. Now, you guys are computer science majors, so let me give you the importance of this and including the next section 2.5. Here's the deal. We like to have computers do this kind of stuff for us because it gets kind of painful after a while. We're not going to argue that point. So, here's the idea. you know, it's okay when we have a 2 by 2, a 3 by 3, a 3 by 5, a 5 by 2. That's fine. What happens when we have matrices that are bigger? You know, 12 by 8, 45 by 96, 212 by 5,617 size. You understand, when you get bigger, you don't want to do it, number one, because it just becomes, I mean, you're understanding the process now, but yes, having some type of program to be able to multiply matrices out is going to be very advantageous. So let's talk about programming for a second. Now, the larger the matrix you got, the more pretty much CPU time it's going to take to actually get the solution, right? So the other thing that we're going to be looking at is from a computer science perspective, how can I shorten up the process? Granted, an algorithm, but if we can shorten up the process to actually make the time to actually get the solution shorter, even from a computer perspective. We don't want to watch the computer and watch it spin for a while. How many times we do that every time we're on the internet or whatever? We don't want to sit there and watch this thing spin. We want to type it in and quickly be able to chunk us out the answer. So we need to cut down the amount of time the computer takes to be able to do said program. One of those features is going to be what we call partitioning of matrices. Now, this one right here, I thought I'd help you out with this, and I went ahead and multiplied it out for you guys so you don't have to copy them. But I got two matrices. And again, just think about the size here. This is a 2 by 3 matrix times a 3 by 2 matrix. My matrix here, the first one is 1, 3, negative 2, 6, 1, 4. I'm multiplying it by negative 2, 0, 4, 1, 1, negative 2. Matrix A times matrix B, the sizes are right to be able to multiply. 2 by 3 times a 3 by 2. The number of columns on the first matrix match to the number of rows on the second matrix. They match and cancel, so my resultant is going to be a 2 by 2. Row by column. 1 times negative 2 plus 4 times 3 times 4 plus negative 2 times 1. 1 times negative 2 is negative 2. 3 times 4 is 12. Negative 2 times 1 is negative 2. Okay, there's your first row, first column position. First row, second column. 1 times 0 is 0. 3 times 1 is 3. 2. Negative 2 times negative 2 is 4. That's 3 plus 4. Second row, first column. 6 times negative 2 is negative 12 plus, there's your negative 12, plus 1 times 4 is 4, plus 4 times 1 is 4. Negative 12 plus 4 plus 4. And then second row, second column. 0 times 6 is 0. 1 times 1 is 1. 4 times negative 2 is negative 8. So that's 1 minus 8. So negative 2 plus 12 plus minus 2 is going to be what? 8. 3 plus 4 is 7. Negative 12 plus 4 plus 4 is negative 4. 1 minus 8 is negative 7. And there's my resultant matrix. Okay? But is there a way we could shorten this thing up? Okay? And so, what we're saying here is this. If we could somehow block these matrices off, I mean by we got this big matrix, and you don't only want to do this if the things are oversized, okay? If they're small enough, this wasn't that bad. But instead of being 2 by 3 and 3 by 2, let's say it's 20 by 30 and 30 by 20, then you can begin to see why it's advantageous to do this. We want to partition the matrix. So if you've got this big matrix, and they don't always have to be the same size, but if we somehow take a big matrix and subdivide it up, okay? So this is matrix A, and these guys don't have to be the same size, but I do have to partition it in such a way that when I do my partitions, I'm going to be able to multiply the internal matrices together, okay? So, and I'll talk about exactly what I'm doing in just a second. So I've got this guy right here. So I've taken this big matrix here and put it into 4 blocks. A11 matrix, A12 matrix, you know, A21 matrix, and A22 matrix. We subdivided it. And over here on my second matrix, something like this, I'm just going to put it right down the middle and say this is the B1 top matrix, this is the B2 bottom matrix. But again, I do have to pay attention to size on these things so that I can make sure I multiply this out. So in reality, what we're really doing here is having matrices of matrices. All right, think about that concept for a second. This is a matrix. What's in the entries? Integers. You didn't even do fractions here, just integers, right? What if I do a matrix and the entries inside the matrices are my matrices? Again, I want you to expand your mind in terms of being able to see what you can do with this stuff. So you're used to doing things like this. A11, A12, A13, A21, A22, A23, A3, where the A little ij's come from the real numbers, right? Classic matrix. This sucker is what? 3 by 3. That's what I meant. Okay? I do this. 2, 1, 3, 5, 6, 7, 2, 8, 1, 0, 1, 1, 3, 6, negative 1, 1, 2, 1, 2, 3, 4, because I have no imagination. 5, 6, 7, 8, 9, 12, negative 1, 5, negative 6, negative 7, negative 8. Okay. I got matrices inside of matrices. You see what I'm getting at here? So, this is a 3 by 3 matrix. But I put in each one of these entries, I put another matrix. I have to have them all the same size. So really, what size matrix is this guy now? He's actually 3 times 2 is 6 by 6 now. Okay? I doubled the size of this sucker by, instead of just putting real numbers here, I put a matrices in for each position. No, where does it say that the entries have to be real numbers? No, I can put all kinds of stuff. I can put complex numbers. I can put matrices inside of matrices. So then you begin to expand on what can be done with this, and especially from a computer science perspective of this idea of partitioning your matrices. You have a question?
So did you say that when you have matrices and matrices, they have to be the same size?
No.
But in this one, you stated like maybe.
Okay, fine. 2, 1, 3, 5. 6, 7, 0, 1, 2, negative 1, 1, 3. It's negative 1, 1, 2. I couldn't read my hand. 9, 10, 11, 12. Okay? And then I can have this big old matrix. 1, 2, 5, 6, 3, 4, 7, 8. Negative 1, negative 2, negative 5, negative 6. Negative 3, negative 4, negative 7, negative 8. They like them balanced, okay? Are they the same size? No, I can partition these guys however I want. I mean, so this one's a 2 by 2. This one is a what? 2 by 4. This one is a 4 by 2. This one's a 4 by 4. So you know, so I got, instead of having 9 matrices, I put it into 4 matrices, but they're not all of equal size. Does that make sense? So what I am saying is this, back over here to this example. If we do some type of partitioning, and again, the ultimate goal is to multiply. Question, yes?
What's the size of our new matrix?
What's the size of a new matrix? Well, it depends on what kind of matrices you chunked into these guys here, but they are going to have to be such that this thing is going to have to be some type of size that you can actually multiply. This one, again, is still 6 by 6. I know that's 2 by 2, that's 2 by 4. This one is 4 by 2, this one's 4 by 4. But if you put them together, you can actually see the entries. I mean, we're just partitioning it up, but this is still the same big matrices, and just don't write the little blocks on them, and you can see it's a 6 by 6. But I'm telling you, I can group them together differently in terms of different size matrices if I need to, okay? Go ahead.
For the, not the one on the right, but the one on the left, how did you get a 6 by 6? How did you get a
1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6. There are, if you mash it all together, there are 6 6 rows, and there's 6 columns. Okay? Again, we're augmenting within the augmented, this is what we're slapping matrices inside of these things. That's really what we're doing. So, but my point is this. All right, if you do subdivide this, now, so you're kind of looking at something like this, but this was kind of small, and we really didn't need to partition the thing out. But if the thing is actually big enough, partition these guys in such a way that, so I put 4 of them here, so A11, A12, A21, A22, and again, in terms of my example, this would be like A11, this would be A12, this would be A21, this would be A22, okay? And I took over here and I just made this B1 on top and B2 on bottom, okay? Now, multiply. To multiply, I'm going to do row by column. A11 times B1 plus A12 times B2. That would be like first row, first column position. A11 times B1 plus A12 times B2. That would, when the resultant would actually go here. It'll be a matrix inside my matrix. Down here, second row, first column, because there's only one column. A21 times B1 plus A22 times B2. A21 times B1 plus A22 times B2. This would be a matrix down here. There'll be a matrix on top, matrix on bottom, and then that would be my solution. If you get rid of the matrix looking thing, you can look at it as a big picture of one big matrix or matrices within inside of matrices. Okay? This is the idea of partitioning stuff. So, it's not a hard concept here, but it can be a little bit of a pain. So, let me give you an example. Here's one. Partitioning of a matrices. So, got 2, okay, now, in the world of math 2164, these are huge matrices. Let me show you. This is a 3 by 5 by 5 by 2. Once you start getting 5, 6, 7, 8, 9, 10, these things get, if you notice, 4 by 4 is all we've ever done. Occasionally I'll throw a 5 by something at you, but I will help you out with some of the row reduction tools like I did on the test and stuff. But, but then you got to expand your mind. Instead of 3 by 5, I'm looking at 30 by 50 or 300 by 500 or something like that. These things can get big quickly. So, but the process. So I've got this 1, -3, 1, 0, -4, 1, 5, -2, 3, -1, 0, -4, -2, 7, -7. So this is 3 by 5. And then I got this other matrix B, which is 5 by 2. 4, 6, -2, 1, -3, 7, 1, 3, 5, 2. Okay? So, what I would like to do is I want to partition these particular matrices in such a way that I could make smaller matrices and multiply those out and then be able to get the big resultant answer. So, the trick is, how do I do that? So, on this one, okay, I would do something like this. Partition it right down here. Okay? But this is still 3 by 3. It's still a little bit big for me. So I'm going to partition the bottom one off. Like such. Okay? First, I decide on my first matrix how I'm going to partition it up. Now, before I come over here to talk about this one, I want to look at this guy. What size is this sub-matrix? What size is it? It's 2 by 3. I'm going to put him right here in the corner with little parentheses here. 2 by 3. What size is this dude? Clearly 2 by 2. What size is this one? 1 by 3. Size is this one? 1 by 2, right? So what I now have is really a 2 by 2 matrix, but I got matrices inside of my matrices. The resultant is still 3 by 5. Does that make sense? Now, here we go. If I'm going to multiply row by column, how do I want to partition this? Because remember, this is 3 by 5, this is 5 by 2, so I can officially multiply these matrices together, right? I'm just trying to do it in a partition sort of way. So, I want to multiply, this is my first matrix here, I want to multiply something over here. What size is this guy? 3 by, 2 by 3, right? This has got to be what, over here, to be able to multiply. If I was going to look at this guy here, what do I need to multiply this guy by? 3 by somebody, right? It's got to be 3 by somebody. That's my point here. Because this is 2 by 3, this is going to have to be 3 by somebody. So, I need at least 3. 1, 2, 3. So this is where I got to cut him off out. You understand? The way I partition this guy forces how I have to partition the second guy. Does that make sense? This one is what size now? He is 3 by 2. So I can multiply this one together, right? Row by column. And then if you do it down here, this is a 2 by 2. I must leave this guy. This is also a 2 by 2, right? I can do a 2 by 2 times a 2 by 2. And so this first one's going to happen. Now I got to check the second row. This one is a 1 by 3, right? But this one is a 3 by 2, so I can multiply those two guys together because the 3's match up, so they're going to cancel. So I'm left with a 1 by 2. And then the second one is a 1 by 2. This is a 2 by 2. So a 1 by 2 times a 2 by 2 is going to be another 1 by 2. But how I partition this guy dictates how I have to partition this, make sure these guys line up. So let me give you the scenario here. Because I partition this big matrix A here as such, this is now A11, A12, A21, A22, right? This is the matrix A here, okay? Times matrix B. We only partition this guy this way, so it's a little divide here. I'm going to call him B1 and B2. Now, what? No, forget this for just a second. Let's look at this partitioning of a matrix. How would I actually multiply these guys together? Row by column. It's for the first row, first column position. It's going to be A11 times B1 plus A12 times B2. That's going to go here. Does that make sense? And then underneath it, because it's one, this is like by 1. Underneath it's going to be A21 times B1. A21 times B1 plus A22 times B2. And this would end up being my answer. Now these are going to be matrices, matrices inside of matrices. We're really trying to get you guys to expand your knowledge base on how you can apply this stuff. Okay? Nowhere do we always have to have numbers inside of matrices. I can put other kind of functions in there too. And matrices inside of matrices is really a great aspect here of expanding this concept here. So, here we go. You see this? I'm going to subdivide and give these guys names. This is A12. This is A11. This is A12. This is A21. And this one is A22. This top one's going to be B1. Bottom one's going to be B2. I gave them names now. Okay? So, let's do this. What is A11 times B1? That would be, A11 would be this 1, negative 3, 1, 1, 5, negative 2, times B1. B1 is this 6, 4, negative 2, 1, negative 3, 7. Okay? Plus A12 times B2. Who is A21? A12. A12 is the 2 by 2. 0, negative 4, 3, negative 1. Times who's B2? That's the 2 by 2. 1, 3, 5, 2. And notice these sizes, I rigged it such that these sub-matrices can be multiplied together because they are the right size. I wrote my partitions here, which dictated how I had to subdivide the B matrix over here. Does that make sense? Okay? So let's go ahead and do this first part over here first. What do I end up getting here? Row by column. With me? All right, I'll just do this in my head. 1 times 6 plus negative 3 times negative 2. 1 times 6 is 6. Negative 3 times negative 2 is 6. 6 plus 6 is 12. And 1 times negative 3 is negative 3. 12 minus 3 is none. Agreed? First row, first column. First row, second column. 1 times 4 is 4. Negative 3 times 1 is negative 3. 4 minus 3 is 1. And 1 times 7 is 7. So 1 plus 7 is 8. Keep going. 1 times 6 is 6. 5 times negative 2 is negative 10. 6 minus 10 is negative 4. Negative 2 times a negative 3 is 6. And I forgot what I just did. So what's 6? Negative 10. Negative 10, that'll be minus 4. Yeah, minus 4 plus 6 is 2. And then row by column, 1 times 4 plus 5 times 1 plus negative 2 times 7. So that's 4 plus 5 minus 14 is negative 5. You'll also notice what I'm doing. I'm doing this stuff in my head. So there's only so big a size that I can give over this crap in my head before I have to start writing even stuff, some other things down. So another reason for understanding this stuff. All right, and add that to this guy. This one is, this was a 2 by 3 times a 3 by 2, so it was a 2 by 2 answer. This one is a 2 by 2 times a 2 by 2, so this is going to be another 2 by 2 answer. 0 times 1 plus negative 4 times 5, negative 4 times 5 is negative 20. 0 times 3 is 0, negative 4 times 2 is negative 8. And zeros in my matrices, in case you didn't know. Row by column, row by column. Second row, first column here. 3 times 1 is 3, negative 1 times 5 is negative 5, 3 minus 5 is a negative 2. And then 3 times 3 is 9, negative 1 times 2 is negative 2. 9 minus 2 is a positive 7. Now you can put these two guys together, and what do we get? Here we go. What is 9 minus 20? 8 plus negative 8. That was 0. 2 plus a negative 2. That was 0. And negative 5 plus 7 is 2. Agreed? Wait, not done yet. Now I want to come over here and do this second one. This is the A21 times the B1 plus A22 times the B2. All right. A21 was this guy right here. It is the 0, negative 4, negative 2 times B1. B1 is this guy here. 6, 4, negative 2, 1, negative 3, 7. Plus A22. A22 is this guy. He's a 1 by 2. 7 and negative 7. Times the B2. B2 is right here, which is the 1, 3, 5, 2. Does that make sense? So let's go ahead and do this one. This one is a 1 by 3 times a 3 by 2. What's my resultant going to be? By 3 times a 3 by 2. 1 by 2. 1 by 2. First row, first column. 0 times 6 is 0. Negative 4 times negative 2 is 8. Negative 2 times negative 3 is 6. 8 plus 6 is 14. First row, second column. 0 times 4 is 0. Negative 4 times 1 is negative 4. Negative 2 times 7 is negative 14. Negative 4 minus 14 is negative 18. What about this guy? This is a 1 by 2. This is a 2 by 2. I'm going to get another 1 by 2. I got to be able to add them, so they got to be the same size. 7 times 1 is 7. Negative 7 times 5 is negative 35. Negative 7 minus 35 is a negative 28. 7 times 3 is 7. Negative 7 times 2 is 14. 7 times 3 is 21. Negative 7 times 2 is negative 14. So 21 minus 14 is 7. Add them together. Negative 14 plus 28 is a negative 14. Negative 18 plus 7 is negative 11. Does that make sense? Now, back to the actual answer. If I multiply this big matrix times this big matrix, you're going to get this matrix, which is this. A11 times B1 plus A21 times B2 is this resultant here. Okay? So this is that negative 11, 0, 0, 2. And then the second positioning over here is the A21 times B1 plus A22 times B2, and we got the answer of -14, -11. Okay, so putting it together, I get -11, 0, 0, 2, -14, -11. And notice, this thing was 3 by 5 times a 5 by 2. The answer is a 3 by 2. This is the actual answer. And I know what you're thinking. Geez, Dr. Taylor, is that actually even any faster than me just go ahead and multiply these two matrices together? Well, I want to remind you, no, probably not. But this one is 3 by 5 times a 5 by 2. And I'm trying to show you the partitioning idea. Imagine now it is 30 by 50 times a 50 by 22 or something like that. So something huge. When you start getting bigger, you will discover that this partitioning method to take these big matrices and subdivide them into smaller matrices and then work out the smaller matrices out of it will be very advantageous and actually be faster, not only from a personal perspective, but from a computer perspective when I'm sitting there taking these big matrices on the old calculator. You know, so for example, okay, got a question for you. This is an awesome calculator. What size matrix can I actually put in this thing? Well, I don't know. Let's see. Matrix, edit A. I got 3 by 3. Could I do a 30 by 30? I can, but I'll never be able to get to the end of this thing and be able to see these matrices or something like that. I mean, there is a point that these things get too big. I mean, look at your screen on your monitors. I mean, if I'm talking about 30 by 50, I mean, I'm going to have to shrink down my font size to be able to look at this thing. And then instead of 30 by 50, I'm talking about, you know, things like, 500 by 7,000. I mean, there's a point that even your screen can't handle the amount of data and stuff like that. But to be able to do something like this, you are talking about huge. So it is very advantageous to be able to do this type of thing, especially with the big matrices stuff. Yes, ma'am.
Can you say again how you did this split up A at the very start, like where it would all work out?
Well, I decided to cut it here and cut it here. What if you decided you wanted to cut it here and cut it here? Would it have made a difference? Yes. You, instead of putting it here, you would have to put the line up here. You dictate how you want to cut a thing. But once you figure out how you are partitioning, proper word, A, it will dictate how you have to partition B to make this stuff work out. So I decided just, I was pretty close to the middle, and the thing looks pretty big, so maybe if I can cut it in half. And then off the bottom, it's 3 of them, so I just cut off the bottom row there, because it's odd number. So I just decided to go there and there is really what I did. But I could have changed it. I could have put it here and over here, or something like that. Or even here and up here if I wanted to. But if I did, that would dictate how I have to partition this to make sure that this is your A1, A2, you gotta multiply this times this. So if you put your partition line up here, for example, this would now be a 1 by 3. This would have to be a 3. I mean, basically, you would have to figure out exactly what size this thing has to be to be able to multiply it out. So you can pick anything you want to here, but once you pick it here, it will dictate how you have to literally subdivide the partition the B up to make the things match up so you can actually put the bottom together. Does that help? All right, so based upon that, can we make them a little bit better? Here we go. Also note, if you have a matrix of this form, A11, A12, 0, A22. Now remember, I'm looking at this as a matrix that's been subdivided, partitioned up. So I'm kind of looking at a general form here, where this is what we would call upper triangular. So down here in the bottom part, it's going to be zeros. And so I've got these, partitioned out A11 matrix here, A12 matrix, A22 matrix down here. So, but you got zeros down here on the lower left, like you may have done a little bit of row reduction on that sucker. You swept down a couple of times and you just gave up after a while. And so I get something that looks like this. With me with zeros down here in the lower left-hand corner. And you want to be able to find its inverse. Is there a particular way? Now again, think about it from a partitioning and from a very, very large matrix perspective. But you've got zeros down there. So, you want to find the inverse. In other words, you want to find a B matrix such that A times B is equal to the identity matrix. You with me? That's really the whole idea behind finding the inverse, is when you multiply it times the original A matrix, you take B, multiply it times A, you will get the identity. Identity is ones on the diagonal, zeros off the diagonal. Okay? So, and I've subdivided, making it look the same way. Now, this was given to me. A11, A12, 0, A22. Okay? Now, this B matrix, I don't know what he's going to look like, but since this was subdivided into a pretty much 2 by 2, I'm going to subdivide B in something similar as a 2 by 2. B11, B12, B22, 21, B22. And when you multiply them, you're going to get the identity matrix. But the identity matrix can be partitioned up. This will be identity with P entries on it, and then with Q entries on it, because I'm not sure exactly how I partition them up. So these may be different identities, but it's one big identity. One's on the diagonal, zeros off the diagonal. Where? Now, I've set this thing up. This is A times B, and this is equal to the identity matrix. Now, to make this thing work, row by column, A11 times B11 plus A12, row by column, it's got to be multiplied by B21, okay? S, A11 times B11 plus A12 times B12 has to be equal to the first row, first column position. That's going to have to be equal to IP. Keep going. Let's see here. First row, second column position. A11 times times B12, this guy, plus A12 times B22, that's going to have to be equal to the 0 partition, 0 matrix, if you see. So I'm doing this row by column, and I'm setting equal to this. So A11 times B11 times A plus A12 times B21 has to be IP. A11 times B12 plus A12 times B22 has to be 0. Keep going. Second row, first column. 0 times B11 plus 0 times B11 plus A22 times B21. That has to be equal to 0. But this one, you don't need to write that because that's 0 anyway. 0 matrix times anybody is going to be the 0 matrix. So I have pretty much A21 times B21 has to be 0. And keep going here. And then, let's see here. One more. Second row, second column position. 0 times B12 plus A22 times B22. That has to be equal to the identity, whatever Q size that happens to be. This will be a different size than this one up here because I partitioned it up. But you don't care about 0 times anybody. You with me? So it's just row by column, looking at matrices. Now, from this, what can we say? Okay? Now, we're trying to find pretty much the inverse here. I have got A22 times B21 equals 0. Remember, we're trying to find the inverse of this particular matrix. So if this guy is invertible, each one of these little guys is also going to be invertible. The submatrix of the matrix is also going to have to be invertible. So how do I solve for B12? I'm going to multiply by A22 inverse on both sides. Okay? A22 inverse on both sides. So this will end up canceling, and that would give me B21 would have, what's A22 inverse, some matrix, times 0. What's anything times 0? 0. So that tells me right there the B21 matrix, in terms of my setup, that's going to have to be a 0. Keep going. I got this guy right here. I have A22 times B22 is equal to IQ. I'm going to multiply by A22 inverse on both sides. This will cancel, give you the identity, which gives you B22 times the identity, which is B22, is equal to A22 inverse. When you multiply by the identity, you get the other element back again. So that automatically tells me B22 is going to have to be equal to A22 inverse in terms of my setup. And then wait, we got these other two guys. Let me bring this guy down here. I've got A11 times B11, A11 times B11 plus A12 times B21 equals the identity P. But then I could substitute this guy here, so wait a minute. All right, so this is A11 times B11 plus A12. Who is B21? Who's he equal to? Times 0 has got to be equal to IP. So that's going to go away. That gives me A11 times B11 equals IP. Solving for B11 by doing A11 inverse on both sides, I get B11 equal to A11 inverse. So I've got him. And then the last one over here, I got A11 times B12 plus A12 times B22 is equal to 0. Okay, but this is A11 times B12 plus A12. Who is B22 equal to? A22 inverse. That's just substitution there. Okay, so I'm going to solve for B12. It's equal to 0. I'm going to move this term to the other side. So this gives me A11 times B12 equals negative A12 times A22 inverse. Now, how do I solve for B12? I'm going to multiply by A11 inverse on both sides. And remember our properties. What happens to constants? So this will cancel. You get B12. Constants can always be pulled out front. This will be A11 inverse times A12 times A22 inverse. So you've got this guy. So, what's the big deal? So this big A inverse, which was equal to B11, B12, B21, B22. What does he really look like? He would be equal to B11 is A11 inverse. Okay. B12 is this guy here, negative A11 inverse, A12, A22 inverse, inverse there. The B21 was 0, and then the last one is the B22. He was A22 inverse, and this is what the inverse using partitions would actually look like. If your original matrix looked like this is what the inverse has to look like. It is using the algorithms of the property of how to subdivide these guys, matrices within inside matrices. Now, this idea of subdividing it and breaking them up, one last thing before I let you go, and that is our section, and a definition here. Okay, that particular matrix here is this. It is called a block diagonal matrix. You know you're in trouble because we've got names for this stuff. The block diagonal matrix is a partition matrix with 0 blocks off the main diagonal of blocks. Note that such a matrix is invertible if and only if each block of the diagonal matrix is invertible. This is called a block diagonal matrix, and each one of these guys is actually invertible, and this is how we ended up getting, quote, what the inverse actually has to look like, a block diagonal matrix. The last thing, and I obviously didn't get to today because I'm over time, is something called factorization of matrices. how we can take matrices and basically factor them to make them a little bit easier. It is called LU decomposition or factorization, and we'll talk about that on Tuesday. Study hard, and I'll see you guys next. And like I said, you've got enough information in you now, you can do most of your homework that's up on homework number 3. So study hard, see you guys then.